Welcome to this video presentation on the linear time computation of runs over general ordered alphabets. My name is Jonas Ellert, and in the next 20 minutes or so I would like to present to you the results of joint work with Johannes Fischer. Runs, or maximal periodic substrings, are a concept of repetitiveness in strings. In this example here, the yellow substring is in fact a run, because it satisfies two important properties. The first one is that it is a repetition. That simply means it can be written as the at least 2 times concatenation of a shorter substring. In our example, we have the 2.6 times concatenation of the substring BCABA. Since this substring has length 5, we say that the run has period 5. The second property is that the run is maximal. It cannot be extended either to the left or the right. If you compare the symbols at positions 2 and 7, you find different symbols. So extending the run to the left would break the period 5. In the same way, we have different symbols at positions 11 and 16, so extending the run to the right also breaks the periodicity. Runs are a very fundamental way of capturing repetitiveness in strings, and as such they have been well studied in the past. Banai and others show that any string of length n contains at most n runs. The first linear time algorithm to compute all of the runs in any given string was presented by Kolpakov and Kucherov over 20 years ago. However, the algorithm only works for linearly sortable alphabets. We have come pretty close to linear time for general ordered alphabets though. Crochemont and others have an algorithm that runs in n times alpha of n time, where alpha is the extremely slowly growing inverse Ackermann function. With our new paper, we finally achieved linear time even for general ordered alphabets. The remainder of this video presentation is structured as follows. First, I will talk about the different alphabet types and their implications for the time complexities of algorithms. Then I will show how to reduce the problem of computing all runs of a string to computing a sequence of so-called longest common extensions, or short LCEs. The linear time computation of these LCEs is the core of our linear time runs algorithm. Finally, I will also discuss some practical aspects of our algorithm. So let's start by discussing the different alphabet types. In string algorithmics, we oftentimes assume that we are given a linearly sortable alphabet. That means that given a string of length n, we can sort the n symbols in order of n time. It includes the practical case where we have a polynomial integer alphabet. General ordered alphabets are more restrictive. There is still a total order on the symbols, and we can test the order of any two symbols in constant time. But linear time sorting is no longer possible. Of course, we can reduce a general ordered alphabet to a linearly sortable alphabet by simply using comparison sort on the symbols. But this takes n times log sigma time, where sigma is the size of the alphabet or the number of distinct symbols in the string. General unordered alphabets are most restrictive. There is no inherent total order on the symbols anymore. Instead, we can only test the equality of any two symbols in constant time. We can impose an arbitrary order on the symbols by just creating a list of distinct symbols and then replacing each symbol with its position in the list. This way we do obtain a linearly sortable alphabet, but the reduction takes n times sigma time. The different alphabet types have implications on the time complexity of algorithmic problems. Here we are looking at two of the most common problems in string algorithmics, computing the Lempel-Zwift decomposition and suffix sorting. For linearly sortable alphabets, we can achieve optimal linear time. For general ordered alphabets, we could use our reduction technique and achieve n times log sigma time. In fact, there are matching lower bounds for this, so we cannot do any better than using the reduction technique. We have the same picture for general unordered alphabets, where we achieve n times sigma time with the reduction technique, and we have a matching lower bound again. So in a way, it's a bit surprising that we have a very different situation for the computation of runs. As I mentioned earlier, we can achieve linear time over linearly sortable alphabets. With our new result, we can also achieve linear time over general ordered alphabets. And even for general unordered alphabets, we can achieve n times log n time. For example, by using a straightforward modification of an over 25-year-old algorithm by Main and Lawrence. So this means that computing all runs over a string takes fewer character order comparisons and fewer character equality comparisons than computing the Lempel-Zwift decomposition or computing the suffix array. Next, I will show how to reduce the computation of all runs to computing a sequence of longest common extensions. Our example from the introduction should be well suited for the purpose. The key insight is that every run with period p contains either a next smaller suffix edge or a next larger suffix edge of length exactly p. In our example, we have this next smaller suffix edge from position 5 to position 10. It means that suffix 10 is the first suffix that starts to the right of suffix 5 and also is lexicographically smaller than suffix 5. Let's look at this in detail. Suffix 5 begins with the symbols A, B, A, B, C, A, B. Suffix 6 immediately starts with a larger symbol and is therefore lexicographically larger than suffix 5. Both suffix 5 and suffix 7 begin with the prefix AB, which is then followed by a larger symbol, the symbol C, in suffix 7. Therefore suffix 7 is also lexicographically larger than suffix 5. Now we have the suffixes 8 and 9, which once again start with larger symbols and are therefore lexicographically larger than suffix 5. Finally, we have suffix 10. Both suffix 5 and suffix 10 start with AB, AB, C, A. In suffix 10, this prefix is then followed by the symbol A, which is smaller than the symbol B in suffix 5. Therefore, suffix 10 is the next smaller suffix of suffix 5. Given our next smaller suffix edge, it is easy to find the borders of the run. Let's start with the right border. We simply look at the suffixes at positions 5 and 10. Now we try to find the longest common prefix between the two suffixes. This can be done by just simultaneously scanning the two suffixes from left to right until we find the first mismatch. In our example, we have a shared prefix of length 6, and then we find the mismatch. So we know that the run ends at position 10 plus 6, over here the 16, which breaks the periodicity. We call this the longest common extension of the positions 5 and 10, with subscript r because we're going in the right direction. We can also do this for the left direction. Here we look at the two prefixes ending at positions 5 and 10. Now we scan from the right to the left and try to find the first mismatch. We find a shared suffix of length 3, and then we have the mismatch. So we know that the left border of the run is at position 5 minus 3 equals 2, over here. We denote this by LCE with subscript L of positions 5 and 10. Of course, we cannot actually afford to compute all of the LCEs by naively scanning in the text. I will show a much more efficient way in a minute. But before, I want to show you a simple runs algorithm that is based on the computation of these LCEs. We start by pre-computing all of the next smaller suffix edges, which takes linear time even for general ordered alphabets. Then we look at one index I at a time and investigate its next smaller suffix at position j. If the next smaller suffix exists, then we know that we're looking for a run with period j minus I. Using the technique from the previous slide, we compute the left and the right border of the run. Only if the resulting interval has length at least 2 times the period, we have found a run. Finally, we have to repeat the entire process, but this time with the next larger suffix edges. It is clear that this algorithm takes linear time apart from the time needed to compute the longest common extensions. For linearly sortable alphabets, we can spend linear time on a pre-processing and then answer every longest common extension query in constant time. For general ordered alphabets, there has also been quite a bit of research aimed at making the longest common extensions faster. Kosolobov showed that any sequence of n longest common extension queries can be answered in n times log to the 2/3 of n time. This was improved shortly after by Gawryczowski and others, who showed that actually n times log n time can be achieved. Finally, Krushmo and others exploited a special non-crossing property of the LCEs. This resulted in n times alpha of n time. Now I will present our new linear time algorithm for computing the LCEs. In the presentation, I will only consider the left direction. Our algorithm for the right direction is quite similar, but it has some subtle technical differences. For the left direction, we consider the next smaller suffix edges in decreasing order of their start positions. At all times, we keep track of the leftmost already inspected text position. That means that at any point in time during the algorithm execution, we have the following picture. The next index we want to consider is index I. That means we want to compute the LCE between I and its next smaller suffix. The leftmost position we have already inspected is position C, and we inspected it during the LCE computation between I' and J'. The LCE is highlighted by the substring alpha here. For the presentation, we just assume that the two occurrences of alpha don't overlap. In the paper, we also consider the case where the two occurrences do overlap. This does not need any special handling by our algorithm. In fact, it only slightly complicates the proof of correctness. Assume that the suffix at position j is the next smaller suffix of the suffix at position I. Before showing how to compute the LCE, we show some properties of j. First, we show that j is not contained in the interval between I' and j'. Assume that it is contained in the interval, then we have this red next smaller suffix edge from I to j. By definition of next smaller suffixes, this means that the suffix at position j is lexicographically smaller than the suffix at position I. It also means that the suffix at position I' is lexicographically larger than the suffix at position I. Now we have shown that the suffix at position j is lexicographically smaller than the suffix at position I'. This means that the next smaller suffix edge, starting at I', cannot go any further than j. This is a contradiction, and therefore we have shown that j cannot be contained in the interval between I' and j'. The second property that we show is that j cannot be equal to or larger than j'. Assume that it is, then we have this red next smaller suffix edge from I to j. In the left occurrence of alpha, we have the substring beta from I to I'. Of course, we have the same substring in the right occurrence of alpha, and there it starts at some index k. Since we have a next smaller suffix edge from I' to j', we know that the suffix at position I' is lexicographically larger than the suffix at position j'. Naturally, prepending any prefix to both sides doesn't change the lexicographical order, so let's prepend beta. Now the string on the left side is identical to the suffix at position I, and the string on the right side is identical to the suffix at position k. Since we have shown that the suffix at position I is lexicographically larger than the suffix at position k, we know that the next smaller suffix edge starting at position I cannot go any further than position k. This is a contradiction, and we have shown that the property holds. If we combine the two properties, then we see that j can only be contained in the interval between I and I'. Now we will transfer I and j to the right occurrence of alpha. The two indices I' and j' have the same relative position within alpha as I and j. In the paper we show the property that if there is a next smaller suffix edge from I to j, then there is also a next smaller suffix edge from I' to j'. This means that we have previously computed the LCE between I' and j', because we compute the LCEs in right to left order. Now there are two possible cases for this LCE. It might either be relatively short, which means that the entire LCE and also the mismatching character is contained in the right occurrence of alpha, as highlighted here. Of course, we can transfer the substrings beta and the mismatching symbols back to the left occurrence of alpha, and then it is clear that also I and j have the longest common extension beta with the same mismatching symbol. So this is the best case for us, because it means that we can simply copy the already previously computed LCE value. The second possible case is that the longest common extension between I' and j' is relatively long. It extends at least all the way to the left border of alpha. We will again transfer the occurrences of beta to the left occurrence of alpha. So we see that also I and j share at least the longest common extension beta, and possibly even further symbols as indicated by the substring gamma here. If we run into this case, then we do not scan the two occurrences of beta again. Instead, we skip I minus c character comparisons. This is exactly the length of beta. Then we start scanning naively again, and we scan the two occurrences of gamma. As you can see, the left occurrence of gamma lies to the left of index C, the leftmost already inspected text position. After doing the scan, we will update this position, so it will be to the left of gamma. This is the argument why our algorithm takes linear time, because whenever we do such a scan, we only scan each text position once. The following algorithm summarizes our strategy. It takes the array of all next smaller suffix edges as input and computes all left longest common extensions. At all times we maintain two variables. The first one is the leftmost already inspected text position C. The second one is the distance d between I' and j'. Now we look at one index at a time, starting with the rightmost one and finishing with the leftmost one. For each index I, we then inspect the next smaller suffix at position j. If the next smaller suffix exists, then we can compute I' and j' as seen earlier. Now we check which of the cases actually applies. If the already computed LCE between I' and j' is less than I minus c, then we have a relatively short LCE and we copy it as described earlier. Otherwise, we skip I minus c naive character comparisons and then scan the remaining relevant part. This also covers the special case where I equals c. Finally, we have to update our variables c and d according to the newly computed LCE. This also makes it very easy to see why the algorithm takes linear time. Whenever we scan a certain number of symbols, we reduce c by exactly that number immediately afterwards. Since initially c equals n, this means that by naive scanning, we inspect at most n symbols. I hope I could give you a general idea of our algorithm. Lastly, I also want to discuss some of its more practical aspects. Most importantly, it results in a surprisingly simple implementation of the runs algorithm. Apart from the next smaller and next larger suffix edges, we do not need any other data structures or algorithmic machinery. This also results in a fast practical performance. A preliminary evaluation showed that we achieve a throughput of over 10 megabytes per second for a large variety of different texts.
We evaluated our algorithm on the pizza chili text corpus. The first 6 texts are real texts that might occur in practical applications. We achieve a similar throughput for all of these inputs. The algorithm performs worst when processing DNA sequences, which among the 6 texts also have the highest density of runs. We also looked at some artificial texts that were designed with repetitiveness in mind. Here we achieve the highest throughputs with over 15 megabytes per second. This is somewhat surprising, because the texts almost reach the theoretical upper bound of the maximal number of runs. Finding out how exactly the density of runs influences the performance would require a more extensive evaluation. The source code of our algorithm is publicly available on GitHub.
Our C++ implementation, including the computation of the next smaller and next larger suffix edges, contains less than 250 lines of code. It consists of a single header file and it uses no external libraries, so it should be very easy for you to use it in other projects. To summarize our results, we presented the first linear time algorithm that computes all runs in a string over a general ordered alphabet. It achieves its fast theoretical and practical performance by exploiting special properties of the next smaller and next larger suffix edges, which are essentially just a different representation of the so-called Linden array. If you have any questions, feel free to contact me directly via email. Or if you are watching this presentation before the ICAP 2021 virtual conference event, you are welcome to ask questions during track A, session 6C. Thanks for your attention and see you at ICAP.